Problem 5. A lossless transmission line has a length of 50 cm with L is equals to 10 microhenry per meter and C is equals to 40 picofarad per meter. If it is operated at 30 MHz, its electrical length is option A 28 degrees, B 48 degrees, C 108 degrees and D 40 pi. Now observe the solution for given problem. In the problem, the data given is the length of our transmission line is 50 cm, L, that is inductance per meter, is 10 microhenry per meter, capacitance is 40 picofarad per meter and frequency of operation is 30 MHz. Now we require electrical length. Electrical length is simply defined as beta multiplied with length of the transmission line. So here we are supposed to calculate beta, as length is given to us, we are supposed to calculate the phase constant beta. If you calculate beta, then beta into L is simply said to be the electrical length of our transmission line. Now what is beta for any transmission line? So beta is equals to whatever it may be, that may be either lossless line or distortionless line. Beta is equals to omega root LC. That omega is the angular frequency of that particular line, which is equals to 2 pi f root LC. So f is the operating frequency. Now what we have to do is just we have to substitute frequency here, L here, C here, substitute them, which is equals to 2 pi into what is the frequency of operation, 30 mega, 30 into mega stands for 10 power 6 and under root LC, root L is nothing but our inductance, 10 into 10 power minus 6, that's micro stands for minus 6 and C is 40 pico, 40 into 10 power minus 12. So simply using a calculator you can calculate this much parameter, that is nothing but your beta. Now multiply this beta with L. So beta into L is 50 centimeter, here L is length, 50 centimeter means into 10 power minus 2 meter, then the answer what you will get is 108. So after multiplication of all these things and multiplying that one with our length of our transmission line, that is 15 to 10 power minus 12, we will get 108 degrees as answer. So option C is correct. This is the solution for this simple problem. A certain line having R0 equals to 400 ohms and length L is equals to lambda is open at both ends. The impedance at a point lambda by 4 from one end is option A 0, option B 400 ohms, option C infinite and option D is 200 ohms. Now just to observe the solution for this simple problem. The data given is a line of length lambda is given to us and its characteristic impedance is 400 ohms, right? Just you imagine how the line is. Let us take this is the line with length, a transmission line with length lambda and its characteristic impedance is 400 ohms and the line is open at both ends. It was opened at the load end, it was opened at the input end also. Now we are supposed to calculate the input impedance at lambda by 4 distance from any one of these ends. Since these two are open, no problem, you can swap it. Right, I am calculating from the load end what will be the input impedance at lambda by 4 distance. That what I require. So simply this particular part is said to be a lambda by 4 transmission line. Right, ignore the entire part, just you don't take the remaining part, ignore the remaining part, you take this small part, that what I am considering as a lambda by 4 length transmission line. Now what is the input impedance of a lambda by 4 length transmission line? Admittance. Already we know the load impedance will be transformed as admittance at the input of our transmission line. It was opened, as it was opened, what is ZL? ZL is equals to simply infinite. Since it was opened, the load was infinite. Now, what is input impedance at this particular location? Zn is equals to YL. YL is simply 1 by ZL. 1 by infinite. 1 by infinite is 0. So, clearly, in option A, we have 0. That whenever we are considering a lambda by 4 line length transmission line, then the output will be transformed. That's why it is called as impedance transformer. The output will be transformed as admittance to its lambda by 4 length. So option A is correct answer. Problem 7. A 50 ohm lossless line is terminated by a load impedance of 75 ohms. If the signal power is 100 watt, the power dissipated by the load is. Option A 80 milliwatt, B 20 milliwatt, C 96 milliwatt, and D 4 milliwatt. Now clearly observe what is the data given to our problem. Z0, the characteristic impedance of our line is 50 ohms, load impedance connected is 75 ohms, the input applied to that particular line is 100 milliwatt. Now we require how much power was delivered to the load. So P output we want. For that, just you imagine the scenario. We have a transmission line. Like this, we have a simple transmission line. Don't care about the length since it is not at all required for us. Now we are applying 100 milliwatt input and a load is connected, that is ZL is equals to 75 ohms. A load is connected at the output end. When this 100 milliwatt power is applied to the transmission line, how much power will be absorbed by the load? As we know, definitely there will be some reflection from the load, as this load impedance is not equals to the characteristic impedance of our transmission line. The characteristic impedance is 50 ohms, load impedance is 75 ohms. Definitely some reflection will be there. After reflection, how much amount of power will be absorbed by the load that we want. So P out is equals to how much? For that, you calculate the reflection coefficient. First of all, what we do is just we will calculate how much amount of voltage is reflected. Reflection coefficient is clearly related to the voltage. So the reflection coefficient is VR by V in, that is reflected voltage to the applied voltage, which is equals to, what is the formula for reflection coefficient? Gamma, ZL minus Z0 divided by ZL plus Z0, which is equals to, what is ZL here? 75 minus 50 divided by 75 plus 50. 75 minus 50 is 25 divided by 125, which is equals to 1 by 5. So 1/5 of voltage will be reflected. Don't take this is transmitted, and don't take that one as a power also, voltage. So 1/5 of voltage applied will be reflected from the load. Now how to convert this one into power? As we know, P output divided by P input is directly proportional to, P output is directly proportional to V output square, and P input is directly proportional to V input square. So V naught by V in whole square, or here clearly if you are taking V power reflected, PR here directly it is proportional to VR. Whatever it may be, you can take either P output or V output, P reflected or V reflected, both you can take. So PR by P in is equals to, directly I am writing this one as PR by P in is equals to VR by V in whole square, which is simply gamma square. What is our VR by V in? Gamma square. What is gamma square? 1 by 25. So whenever we are calculating PR by P in, then you are getting 1 by 25 means 1 by 25th power is reflected. It's not transmitted, it is reflected. 1 by 25th times of the power is reflected. So what I want is how much power reflected, I will calculate initially. So P reflected is equals to 1 by 25 times of 100 milliwatts. What is 1 by 25 times of 100 milliwatts? 4 milliwatts. Power reflected is 4 milliwatts, but what we require is power transmitted. Now simply you can observe that power input is equals to power transmitted plus power reflected. Then what about the power transmitted? Power transmitted is equals to P in minus P reflected. So easily you can say that P output is equals to P in minus PR, which is 100 minus 4 milliwatt. This is 100 milliwatt minus 4 milliwatt, which is equals to 96 milliwatt is our answer. So don't get confused to the voltage reflection coefficient and the asked quantity. Here the asked quantity is power, and what we have is voltage reflection coefficient. That's in a hurry. What you will do is you will take this 1/5 as the answer. So simply what you will do is you will calculate this 1/5 into 100, that is simply 20%. 80 minus 100 minus 20, that's simply 80 you will write as the answer, but 80 is not the answer, 96 is the answer because you are calculating its power. So this is a solution for this problem. Problem 8. A short circuit line has Zin is equals to JZ0 by root 3. The length of the line is option A lambda by 8, option B lambda by 6, option C lambda by 12, and option D lambda by 4. Now observe what is the problem given to us. The problem given to us is a lossless line has input impedance of Z0 by root 3. Now we require length of that particular transmission line. Just recollect what is the equation for input impedance of a lossless line under different conditions. When it is short circuited, what is the input? So when it is open circuited, what is the input impedance? For this particular problem, so the input impedance Zin is given as Z0 by root 3, and what is the condition? Simply it is short circuited. Whenever it is short circuited, what is the Zin? Zin is equals to Z0 tan beta L. Now what you have to do is simply you have to recollect what is the input impedance of a short circuit, what is the input impedance of an open circuit line, and make it equals to the given quantity. So Z0 tan beta L, how much it is given as? It is given as just Z0 by root 3. Z0 by root 3. Now equate these two. If you are equating these two, how much you will get? Tan beta L is equals to 1 by root 3. Tan beta L is equals to 1 by root 3. What we got? We require only L, right? Here observe what is beta L. The possible value of beta L is equals to pi by 6. So simply beta L is equals to pi by 6 we want. We don't want, once again, we don't want electrical length. We want only length. For that you need to eliminate this beta. How to eliminate this beta? We have beta is equals to 2 pi by lambda into L is equals to pi by 6. Just beta can be replaced with 2 pi by lambda. Pi will be cancelled, and after simplification what you will get is L is equals to lambda by 12. So the length of our transmission line is simply lambda by 12. So in the option C we can find that one. So option C is right. This is a solution for this problem. Problem 9. A transmission line has an attenuation of 0.3 dB per kilometer. After 10 km from the source, the fraction of power is option A 1 by 2, option B 1 by 3, option C 1 by 4, and option D is 1 by 10. Now observe what is the data given to us. We have a transmission line with attenuation of 0.3 dB per kilometer. We are supposed to calculate how much amount of power will be there after 10 kilometers. The distance which is given as 10 kilometers. So whenever the signal is applied at the input of our transmission line, when it is traveled for 10 kilometers, how much amount of power you can observe? So what is the fraction of that power we require? Very simple one. Just you observe what is the formula for alpha. Simply the formula for alpha is equals to minus 10 log the P output divided by P input. Here clearly remember I am considering it's in decibels because the alpha is given in decibels. Since the alpha is given in decibels, I will consider the formula in dBs, right? That's why I will apply minus 10 log. So which is equals to 0.3 dB. Just you equate these two, then you will get the answer. Minus 10 log P output by P input, that is P applied, which is equals to 0.3, right? After simple manipulation and mathematical observation, you will get P output by P in is equals to 10 power minus 3. That will get this 10 goes to this particular side, and after that one you will get 10 power minus 0.3. That what we will get. Then simply the output power is equals to 1 by 2 times of input power. So after traveling for 10 kilometer distance, you can observe half of the applied power. That the fraction of power observed is 50% or 1 by 2. That's what you can say. This is available in your option A. So option A is right for this particular problem. Problem 10. A line of 75 ohm impedance is terminated with 100 ohms load. Its maximum impedance on the line is option A 100 ohms, B 56 ohms, C 156 ohms, and D is 126 ohms. Just to observe the problem, it's a very simple problem. What is the data given to us? A characteristic impedance of our transmission line is given as 75 ohms. ZL load impedance connected to it is 100 ohms, and we require the maximum impedance on the transmission line. So what is the formula for maximum impedance on the transmission line? Just recollect what we discussed for our input impedance. Z max we require, right? Z max is equals to, simply this can be taken as V max divided by I min. Whenever the numerator is maximum, denominator is minimum, then you can observe the maximum impedance here. So Z max is equals to V max by I min. How to modify this one? V max is as it is that I am writing divided by I min can be written as V min divided by characteristic impedance of the transmission line Z0. The current is equals to voltage divided by impedance V min divided by Z0. So simply this can be written as V max divided by V min multiplied with Z0. So if you want the maximum input impedance on a transmission line, just you can use this formula V max by V min into Z0. What is V max by V min? V max by V min is nothing but the standing wave ratio. So instead of this V max by V min, you can write S. So simply Z max can be written as the maximum input impedance is equals to standing wave ratio multiplied with the characteristic impedance of our transmission line. So easily you can calculate the standing wave ratio from this given data, right? So to calculate our standing wave ratio, we need to calculate gamma. Standing wave ratio is 1 plus gamma divided by 1 minus gamma. So initially calculate gamma and then substitute here. What is formula for gamma? Gamma is equals to ZL minus Z0 divided by ZL plus Z0. What is ZL here? ZL given is 100. 100 minus 75 divided by 100 plus 75. So this is our gamma, that is 25 divided by 175. 25 divided by 175. So simply which is equals to 1 divided by 7. That's what we have here. Now substitute gamma here. Then S becomes 1 plus 1 by 7 divided by 1 minus 1 by 7. 1 plus 1 by 7, how much it is? 8 divided by 6, which is equals to simply 4 by 3. So S is equals to 4 by 3. Don't take that this is the total answer. Z max is equals to S into Z0, that what we have, right? So S is 4 by 3. Now what is Z0 here? Substitute 75 there. Then Z max is equals to 4 by 3 multiplied with our Z0 simply 75 ohms, which is equals to 100 ohms is the answer. This 100 ohms answer is available in your option A. So option A is correct answer. So just you observe what we are doing. We are calculating the maximum impedance. For the maximum impedance, V max by I min is the formula that what I am considering. Now for that, a simple mathematical manipulation will give you the answer. Similarly, if you want Z min, what is the formula you can take? Z min is equals to V min divided by I max. So a corresponding manipulation will gives you the equation for Z min also. So as per requirement, you can take the equation for our Z max and Z min. This is a simple solution for this problem. Problem 11. The position of first maximum of the voltage measured from load on a mismatched line whose gamma is equals to 0.25 angle minus 30 degrees and operating frequency is 2 GHz is option A 11 by 176 centimeter, option B 11 by 176 meter, option C 55 by 16 meter and option D 55 by 16 centimeter. Now observe the solution for this problem. Little bit this is a tricky problem. You are supposed to apply different concepts what we learned in this problem. As there is no direct formula to solve this problem, even though you have a such formula that is little bit complex. What I do is just I will give you how to solve this problem using a simple method. Observe what is the data given to us. The reflection coefficient for the load is 0.25 minus 30 degrees. As in the problem it is given as mismatched line, definitely reflection coefficient will be there. This is the magnitude and this is the phase of that particular one. The operating frequency is 2 GHz. We require the position of first V max. Whenever the particular voltage is traveling on a transmission line, at which location you will get the maximum voltage whenever it is reflected. That's what we want. Now the very simple and very easy one is to use Smith chart. And don't take this Smith chart physically. It is not possible to take the Smith chart physically. You have to imagine how the Smith chart is, and using that Smith chart easily you can observe this, or easily you can solve this particular problem. For that what I do is just I will give you the outline of our Smith chart here. Just you concentrate. Let us take, this is the Smith chart, not the entire Smith chart, just what I took is the outermost circle, that is r is equals to 0 circle I took. Now reflection coefficient is given to us, reflection coefficient is 0.25 angle minus 30 degrees. How to get the reflection coefficient? The magnitude of the reflection coefficient is simply OP by OQ, right? Angle POQ, that what we have, POS, that what we have, right? Or QOS, that what we have. So for that, just you imagine how to observe. Somewhere we have the load. As I know where the load is, I will take ZL here. The normalized load may be somewhere here. Now this is OP, and if you extend this line up to this point, that is OQ, OP by OQ will be equals to 0.25, right? That is the magnitude. And similarly, the angle is minus 30 degrees. What do you mean by minus 30 degrees? We are taking that one in anti-clockwise direction. So this angle is minus 30 degrees. So if you draw a circle like this, then somewhere it meets our S, real axis. So that this is called as the simply or voltage standing wave ratio. This is an imagination that what you have to do. Don't go for exact or physical dimensions or exact values, right? Imagine this is load. From the load, if you are considering the reflection coefficient, OP by OQ will gives you that 0.25, and this entire angle is nothing but the angle POS, right? But instead of taking this entire angle, we are taking the angle in anti-clockwise direction, that is minus 30 degrees, which is given in the data. Now we are at load. So you are at load means you stopped at the load. You are supposed to observe what is the location of first maximum voltage. Now, okay, imagine or just recollect what is the maximum voltage line and what is the minimum voltage line. Here, this is the maximum voltage line. This is maximum voltage line, and this is our minimum voltage line. And from load, when you are traveling towards generator means you are taking a rotation in clockwise direction. Traveling towards generator, take a clockwise rotation. Just you are at load and you are traveling towards generator. Whenever you are traveling towards generator, first you are observing this V min line, that you are observing the minimum voltage, but we don't want that minimum voltage, right? What we require? We require the maximum voltage. So when we are traveling from load to generator like this, after traveling of this much distance, we got Vmax, right? How much distance we traveled? We traveled for a distance of this much angle. Don't get confused. I am saying that distance in angle because you need to correlate it in terms of lambda, right? So here we have traveled for this much distance. What is this distance? 360 minus 30 is simply 330 degrees. So if you travel for a distance of 330 degrees, you will reach first Vmax. So the answer is over. The location of Vmax is equals to 330 degrees. It's a very simple one. But in the options, there are no degrees. Only the lambdas or a simple values are given to us like 11 by 176 or 55 by something, right? So what you have to do is you have to convert this angle into our normal values. For that, correlate once again. So one complete rotation around our Smith chart is equals to traveling of lambda by 2 distance. That is 360 degrees corresponds to lambda by 2, right? Then 330 degrees corresponds to how much? Just simply it is 330 divided by 360 into lambda by 2. That's what we are supposed to calculate. Now what is lambda here? Lambda is nothing but simply C by F. F is given to us, right? So instead of this lambda, I will substitute C by F. 330 divided by 360 into C is 3 into 10 power 8. I directly am considering that one in meters. Later, if required, we will consider that one in centimeters also. Divided by 2 into 1 by 2. That C by 2, that is C by 2 gigahertz. Since it is gigahertz, you need to write down this one as 10 power 9. So this is the simple answer, which will gives you a simple 11 by 176 meter. Take a calculator and simplify this one, then that will be the answer. This is available in option B. So once again, just you observe how I solved this problem. So solving using our normal formula is not at all advisable, that's why it will take a little bit time. So what I do is just I'll take the Smith chart. Using the Smith chart easily you can observe. So since gamma is available, you can replace or represent this particular gamma on our Smith chart. This is the location of ZL as per our gamma. From gamma I represented ZL, and from ZL travel towards the generator. After traveling of 330 degrees, 330 degrees corresponds to this much distance, we will get first maximum on our transmission line. This is the solution for this problem. The total length of a 50 ohm lossless transmission line terminated with a load impedance ZL is equals to 30 plus J15 ohms is L equals to 7 lambda by 20 as shown in figure. The total input impedance across the terminal AB will be option A 38.3 minus J64.8 ohms, option B 19.2 minus J32.4 ohms, option C 64.8 minus J38.3 ohms, and option D 32.4 minus J19.2 ohms. Observe the solution for this problem. A lossless line with characteristic impedance of 50 ohms is given to us, and the load is connected as 30 minus J15 ohms, and the length of our transmission line is 7 lambda by 20. We are supposed to calculate input impedance of our transmission line. So what you have to do is just recollect what is the formula for input impedance of our transmission line. Zin is equals to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. That is for lossless line only. Otherwise you have to go for the basic formula. So once again I will write down that formula here. Zin is equals to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. So this is a simple formula. What you have to do is just a substitution. Z0 is available with us, ZL is also available with us, but beta is not available. L is available. Length of the transmission line is available. So how to get this beta L? Get beta L. The electrical length beta L is equals to 2 pi by lambda. Instead of beta I can write 2 pi by lambda, and the length is given as 7 lambda by 20. So which is equals to lambda will be cancelled, 2 will go with this 10 times, so it is 7 pi by 20. So simply instead of this beta L substitute 7 pi by 20. Take a calculator, substitute Z0, ZL, beta L here. After substitution and simplification of this one, you will get a very good answer. Answer is 32.4 minus 19.2 J ohms as our answer. This is available in option D. So there is nothing except substitution in this particular problem. What you are supposed to do is just you have to take this beta L. Beta L is equals to 2 pi by lambda into 7 lambda by 20, that is 7 pi by 20. This is the solution for this question. After traveling a distance of 20 meter along a transmission line, the voltage wave remains 13% of its source amplitude. What is the attenuation constant in ampere per meter of the transmission line? Just to observe the solution for this problem, this is a very simple problem. Whenever the voltage is traveling in a transmission line, after traveling for a distance of 20 meter, we are getting 13% of the input applied. So whenever the voltage is traveling in a transmission line, what is the basic form? Just to recollect that one. Whenever it is traveling on a transmission line, we have so V0 e power or V0 some amplitude e power minus gamma L. So this is the basic form. As L increases, this entire term decreases. Right, this is purely dependent upon the propagation constant gamma. Here what I am assuming is, the assumption is very important, what I am assuming is there is no phase difference between the input and output, that what I am observing. Therefore beta is equals to 0. If beta makes 0, then what you will get here simply it is V0 e power minus alpha L. Whenever the voltage is traveling along a transmission line, simply it is equals to the magnitude. This V0 is V initial. This is not V output, V initial multiplied with e power minus alpha L. Now bring that one here. V initial e power minus alpha L is equals to how much we are observing? 13% of the initial. Initial is V0. 13% of V0 is nothing but 0.13 V0. So simply make these two equal. E power minus alpha L is equals to 0.13, and here I wrote V output, so I will convert this one as V output, so that you don't get confusion between this V naught and V output. Okay, keep it in mind. So V naught e power minus alpha L is equals to 0.13 V naught e power minus alpha L is equals to 0.13. How much distance we have traveled? We have traveled for 20 meter. So it is minus 20 alpha is equals to 0.13. Take a calculator and simplify this one. You will get alpha is equals to 0.10 Napier per meter. So whenever you are asked to enter the value of that alpha, simply enter 0.10 as it was asked in Napier per meter. Answer is 0.10. That is the solution. A transmission line operating at 5 GHz frequency has characteristic impedance of 80 ohms and phase constant beta is equals to 1.5 radian per meter. The inductance per unit length of the transmission line will be dash nano henry per meter. Just to observe the solution for this problem. What is the data given to us? A transmission line is operating at a frequency of 5 GHz. Its characteristic impedance is 80 ohms. Beta propagation constant is 1.5 radian per meter and we require L. Right? Now for that, just you imagine what are the formula we have. Just you recollect what are the formulas we have for beta and Z naught. The formula for beta is equals to omega root LC. Right? This is the basic formula that what we have. Either whatever that may be the lossless line or distortionless line. And what is the formula for Z naught, which is equals to root L by C. This is also common for both lossless line and distortionless line. So even though he has not mentioned anything, you can use these two formulae. So beta is omega root LC, Z naught is root L by C. Just you multiply them. Beta into Z naught. Beta into Z naught is equals to omega root LC multiplied with root L by C. Simply you will get omega into L. Where L is inductance per meter. That is the quantity that what we require here. Therefore, L is equals to beta Z naught divided by omega. That beta Z naught by omega, beta is available with us 1.5. Z naught is also available with us 80 divided by, instead of omega you can write 2 pi f. So f is given to us. So 2 pi into, instead of f, how much you can write? 5 gigahertz. 5 into 10 power 9. Take a calculator, simplify this one. After simplification, simply you will get 3.81 nano henry per meter. Clearly remember, here you are supposed to identify what are the formula we have to use. There are very simple formula. Just take the beta, Z naught, multiply them, then you will get the required quantity, inductance per meter as 3.81 nano henry per meter. This is the answer for that particular problem. A lossless transmission line is operating at a frequency of 2 MHz. When the line is short circuited at its output end, the input impedance appears to be equivalent to an inductor with value 32 millihenry, but when the line is open circuited at its open end, the input impedance appears to be equivalent to the capacitor with value of 20 picofarad. What is the characteristic impedance of our transmission line? Just to observe the solution, this is a little bit tricky problem. That what is the data given to us? A lossless transmission line is operating at a frequency of 2 MHz, and when it is short circuited at the input, we are observing a pure inductor with a value 32 millihenry, and when it is open circuited, it appears as a pure capacitor with 20 picofarad value. At this instant, what we require is the characteristic impedance of our transmission line with these conditions. So what you have to do is you have to imagine how it is operating. When it is short circuited, it is operating as a pure inductor. Pure inductor is nothing but simply an inductor with positive reactance. Pure open circuited, pure capacitance with negative reactance it is operating. So what will be the Z in SC and Z in OC? That what we require? Just Z in SC, that is when it is short circuited, which is equals to the impedance which is provided by the reactance which is provided by the inductor we are supposed to consider. What is the impedance which is provided by the inductor? It is simply J omega L. For the calculation of omega you can use F, right? So take this one as J 2 pi into, instead of F it is 2 into 10 power 6 mega into L. What is L? 32 millihenry. 32 into 10 power minus 3. After calculation of this one, what you will get is simply J 0.4 ohms. Observe what I am doing is nothing except the simple equivalence. Z in SSC, whenever it is short circuited, simply it is acting as inductor. As it is acting as inductor, I am considering the impedance which is provided by the inductor as J omega L. Nothing more than that. Similarly, Z in OC, when it is open circuited, it is acting as capacitor. So consider the impedance which is given by the capacitor, which is equals to 1 by J omega C. So 1 by J omega C, which is equals to 1 by J, instead of omega, what you can write is 2 pi into 2 into 10 power 6. This is omega. And instead of C, 20 picofarad, 20 into 10 power minus 12, which is equals to simply minus J 3979.9 ohms. That what we will get. If you get Z in OC and Z in SC, getting Z0 is very easy. We have a simple relation. ZSC into ZOC is equals to Z0 square. From that one, you can write Z0 is equals to square root of Z short circuit into Z open circuit. Take this value and this value, multiply them and substitute here. Then what you will get is approximately 40 ohms. So here observation is important. Whenever it is acting as a pure inductor, take the impedance which is provided by the inductor and make it equivalent to the a particular short circuit or open circuit one. And whenever it is acting as a pure capacitor, take the impedance which is provided by the capacitor and make it equals to the corresponding one. Then these two will be useful for calculation of our Z0. So here the answer is 40 ohms. This is the solution for this problem. Problem 16. One end of a lossless transmission line having the characteristic impedance of 75 ohms and length of 1 centimeter is short circuited. At 3 GHz, the input impedance at the other end of transmission line is option A 0, option B resistive, option C capacitive, and option D is inductive. Observe the solution for this problem. This type of line is a lossless line with characteristic impedance of 75 ohms and length of the transmission line is 1 centimeter, operating frequency is 3 GHz. Now we require the type of input impedance. It is a capacitive, inductive, or the combination, 0, infinite, like the different options are given to us. Now we are supposed to examine what is the input impedance for this particular line. So for that, what I do is just I'll take a transmission line. Now for this transmission line, here the condition is also given to us. The condition is it is short circuited. Whenever it is short circuited and with length L is equals to 1 centimeter. So what is input impedance at this particular location? Now for a particular short circuited line, the input impedance is always equals to JZ0 tan beta L. Just you observe what is this JZ0 tan beta L. Depend upon this value, you can say that it is a capacitive load or inductive load or a combination of that one. For that, I will substitute all those things. J, how much Z0 is given to us? Z0 is 75 tan beta. Beta is 2 pi by lambda. 2 pi by lambda into L. L how much is given to us? 1 centimeter. 1 centimeter. Here what we have is a lambda. How to calculate this lambda? Lambda is equals to C by F. Substitute there that one also. J 75 tan 2 pi by, instead of lambda I am writing C by F. 2 pi F into C, that 1 centimeter for temporarily I will ignore. Now observe this one. 2 pi F by C. C is nothing but 3 into 10 power 8. F is how much? F is 3 into 10 power 9. Substitute them, which is equals to J 75 tan 2 pi by 3 into 10 power 8 into 3 into 10 power 9 into 1 centimeter, 1 into 10 power minus 2, that what we have. If you observe this one, this entire quantity is a positive quantity, and if you tan, after simplification and if you take calculator and observe this one, you will get a positive one. So this will be in the form of Jx, that x may be a positive quantity. So simply the input impedance is in the form of Jx. Whenever you are observing a positive reactance, simply you can say that it is the inductive load. right? Whenever you are observing a negative quantity, it is capacitive load. Since we are observing a positive quantity here, this can be taken as the inductive load. That inductive load is available in our option D. So our option D, clearly you have to say that it is inductive type of load. So this inductive load is available in option D. This is the solution for this problem. The characteristic impedance of a transmission line is 50 ohms. The input impedance of the open circuited line is 100 plus J 150 ohm. When the transmission line is short circuited, then the value of input impedance will be option A 50 ohms, option B 100 plus J 150 ohms, option C 7.69 plus J 11.54 ohms, and option D 7.69 minus J 11.54 ohms. Just you observe the solution for this problem. It is very easy. Only we have very simple parameters. Z0 is given, ZOC given, ZSC we require. Right? What is the relation between these three? We have Z0 square is equals to ZSC into ZOC. So if you require ZSC is equals to Z0 square divided by ZOC. What is Z0 given to us? 50 square is 2500 divided by ZOC is 100 plus J 150 ohms. Now I will give you what are the, just to observe the options initially. If you are observing the options, it is a complex quantity, right? In the options, wherever you have complex quantity, identify them, eliminate remaining all. And in the denominator, you have a positive 1 plus J 150 ohms, a plus sign is there. If it goes to, after simplification, if it goes to numerator, what you will get is a negative, right? So this is a simple method with the observation. I am not saying, I am not giving the exact answer, just with the observation, whenever there is such answer, you can pick that one, no problem, right? If there is such answer, only one answer, you can pick it. Otherwise, you have to calculate that one using calculator. So 2500 divided by 100 plus J 150 ohms. After simplification, what you will get is simply 7.69 minus J 11.54 ohms. So this is available in option D. Option D is the correct answer for this particular problem. Problem 18. A lossless transmission line is terminated with a load which reflects a part of the incident power. The measured VSWR is 2. The percentage of power that is reflected back is option A 57.73, option B 33.33, option C 0.11, and option D is 11.11. Already we have gone through a such type of problem. This is also a similar problem but with little bit different data. Just to observe what is the data given to us. The standing wave ratio is given as 2. We require how much amount of power will be reflected, right? For that, from the standing wave ratio, try to calculate the reflection coefficient gamma, right? What is the relation between gamma and standing wave ratio? We have S is equals to 1 plus gamma divided by 1 minus magnitude of gamma. Now which is simply 2 is equals to 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. If you observe this one, you will get magnitude of gamma is equals to 1 by 3, right? The magnitude of reflected voltage, what is gamma here? It is a voltage reflection coefficient. The magnitude of reflected voltage is 1 by, voltage reflection coefficient is 1 by 3. So this 1 by 3 will be equals to V reflected divided by V incident, which is equals to 1 by 3. But what we require is P reflected. It's not V reflected, we require P reflected. So what is the relation between P reflected and V reflected? P reflected by P incident is equals to, directly I am writing the equation, just to ignore the constants. So it is V square reflected divided by V in square, that what we have here. So which is equals to magnitude of gamma square. So what is magnitude of gamma here? 1 by 3 whole square, that is 1 by 9. So directly P reflected is equals to 1 by 9 times of P input. That what you can observe here, 1 by 9 times of P input, that is approximately equals to 11.11%. This 11.11% is available in option D. So this is a very simple problem, that don't get confused again. You may get confused between this voltage reflection coefficient and the asked quantity power. Voltage reflection coefficient is V reflected divided by V input. P is P reflected by P input. There is a slight difference between these two, just you observe them.